Let's jump right into this explainer because there is a massive shift happening in the world of AI right now. We're diving into the energetic paradigm, and specifically how the Ilya Sutskever and SSI thesis completely reframes our approach to superintelligence. We're moving away from the old brute force method of just hoarding raw compute power and pivoting towards something much more profound: engineering safe, governable capability flows. We're not just trying to build bigger brains anymore. We're trying to make them structurally stable and actually safe to deploy in the real world.
To break all of this down, here is our roadmap. We'll hit 1. The limits of raw scaling. 2. The bug A, bug B loop. 3. The energetic paradigm shift. 4. Provers, verifiers, and value. 5. The competitive Medusa trap. And finally, 6. Building governable superintelligence.
All right, Section 1, the limits of raw scaling.
For years, the AI industry has basically run on a very simple, predictable formula. You feed in more data, you pump up the compute and parameters, and boom, you get larger models and higher benchmark performance. Honestly, it turned AI development into a kind of industrial engineering. It attracted massive capital because it was a sure thing. But here's the catch. That success created a severe path dependence. Everyone just clustered around optimizing the exact same familiar architectures instead of asking the tough, riskier algorithmic questions. We basically became experts at scaling up what we already knew. But here is the thing. It's not that scaling stopped working. It's that scaling alone just can't guarantee reliable intelligence out in the real world. There's a huge fundamental difference between benchmark performance and closed-loop intelligence. Think about it. Passing a benchmark is basically like taking an open-book test against known answers. It's static. But real closed-loop intelligence, that means maintaining a stable path through total uncertainty, navigating live feedback, using tools, and dealing with real-world consequences. Just because an AI can write a brilliant essay doesn't mean it can survive a dynamic, changing environment without crashing.
Which brings us perfectly to Section 2, the bug A/bug B loop.
If you've spent any time using an AI coding assistant, you know exactly what I'm talking about here. It's literally like playing a game of whack-a-mole. The AI expertly fixes bug A, but whoops, that patch just created bug B. So you tell it to fix bug B, which it does, only to completely break the first thing and reintroduce bug A. Every single step looks incredibly competent on its own, but the whole interaction is trapped in a totally unstable loop. The AI recognizes the textual pattern of the fix, but it doesn't actually comprehend the underlying system.
Fundamentally, this is a failure of what's called invariant preservation. That's just a fancy way of saying the system needs to maintain what must stay true across a full sequence of actions. The model generates plenty of action, sure, but it lacks the internal discipline to hold the causal circuit stable. It doesn't pause and ask itself, hey, what needs to stay intact after I apply this patch? Or what past failure do I absolutely need to avoid repeating? It has all this solution energy, but virtually zero closure.
So how do we fix that? Section 3, the energetic paradigm shift.
The transition to superintelligence really has to be understood as moving from raw capability accumulation, just piling on more smarts, to governed capability flow. Now, energetic paradigm control, or EP control, isn't just slapping a refusal mechanism on the end of a model like a brake pedal. It's not an afterthought guardrail. It's actually an internal operating grammar. It's woven right into the capability architecture itself to prevent the system's own solution energy from violating prior constraints. Let's contrast two types of agents to make this concrete. Agent A is your classic scaled specialist. It relies on massive, brute force exposure. It's super powerful in familiar settings, but completely brittle the second you take it outside its training distribution because it's essentially just doing memorized search. Agent B, on the other hand, is a generalizing learner. It extracts structure from way fewer examples, prunes its search early, and adapts. What this shows us is that true generalization isn't just hoarding more knowledge. It's actually efficient navigation. It's a much lower-cost way of moving through a complex problem. Right now, reinforcement learning often acts kind of like intense exam pressure. It produces this narrow test prep style performance where the model just learns how to ace the benchmark exam rather than actually understanding the world. To get past that, a stronger system has to juggle multiple constraints all at once: outcome correctness, process integrity, state preservation, uncertainty awareness, and tool use reversibility. The control layer's job is to ensure absolutely none of these are sacrificed just to grab a quick, short-term reward. Let's get into the mechanics of this in Section 4, Provers, Verifiers, and Value. The next massive frontier in AI is shifting compute to inference time, meaning expanding computation when the AI is actually solving the problem, not just during its initial training phase. Instead of relying purely on a giant database of stored knowledge, intelligence becomes a time-extended search. It's literally allocating compute across possible futures, generating and evaluating different paths in real time. But, and this is a big but, without a strong value function guiding it, the AI will just explore a million useless branches. It's like a blind searcher burning through energy in a thick fog. This naturally leads us to the prover-verifier model. It's a completely asymmetric architecture. You have the prover, which acts as the expansion engine, brainstorming and generating candidate solutions. And then you have the verifier, which is the rigorous boundary condition testing those candidates against hard constraints. But here is the absolutely crucial takeaway. For this to work, the verifier must have ultimate, unshakable authority. If its stopping gate can be bypassed, reward hacked, or socially persuaded by a clever prompt, well, that's not control at all. That's just another language generator.
Now, this next part is a truly wild realization. Think about biological intelligence for a second. We actually use emotion, not as irrational noise, but as a highly compressed internal value function. It guides our early search and directs our actions long before we know the final outcomes. AI needs a similarly stable internal guidance system. Since real-world rewards are sparse and often heavily delayed, AI requires a robust value function, acting as an internal steering field, one that simply cannot be overridden or manipulated as the system gets smarter and more capable.
Building right on top of this structural focus is SSI's fascinating resource density argument. Look, a smaller research organization might not have the massive, sprawling total compute of a giant legacy lab, but if they take their compute energy and direct it with laser focus directly at these core bottlenecks, like prover-verifier architectures, that density is what actually moves the needle. It's really not about who owns the biggest supercomputer. It's about how much of your energy is hitting the right unknown without leaking away into distractions. Zooming out a bit, we hit Section 5, the competitive Medusa trap. What happens when we put these systems into the wild? Well, a heavily confined model is safer, but it's less competitively useful. An unconstrained model is highly capable and fast, but wildly destabilizing. This creates a terrifying dynamic called the Medusa trap. It's an incredibly dangerous multi-agent race to the bottom. Imagine Actor A restrains their AI's capability for safety. Actor B removes those limits to win the market. Actor A gets punished strategically for being responsible, which pushes both of them to escalate into totally unsafe risk. It's a system that actively rewards dangerous acceleration.
The energetic paradigm looks at this and says, this isn't just a moral failing, it's a broken system that needs stabilizing. Institutional governance has to step in and fundamentally alter the incentive field. We need strict, shared stabilizers, things like universal evaluation protocols, mandatory compute reporting, secure audit channels, and real liability for autonomous harm. The entire goal here is to literally change the math so that unsafe, reckless acceleration simply does not pay off anymore.
And that brings us to our final section, 6, Building Governable Superintelligence. Just because an AI behaves nicely during a training run does not mean it's actually aligned. We have to look at alignment across 3 distinct levels. Level 1 is behavioral compliance, which is what most current systems do. They smile when the boss is looking. Level 2 is constraint internalization. But the holy grail is level 3, power-stable alignment. That means the system rigidly preserves its safety boundaries even after it gains massive strategic leverage, access to real-world tools, and the ability to self-improve. If we get this wrong, we're looking at a massive, catastrophic risk to human agency itself. Without designs that preserve our participation, we're going to face what's called a bandwidth collapse. Practically speaking, this means incredibly powerful personal agents will be making critical, high-speed decisions for you faster than your brain can even comprehend. You'll become a supervisor in name only, blindly approving outcomes without understanding the mechanics. To prevent this, agents must explain decisions clearly, critical paths must be inspectable, and we absolutely have to retain real, meaningful veto power. So, I'll leave you with this final, provocative thought. The ultimate question posed by the energetic paradigm. The future of AI is not just about blindly accumulating raw capability. It's about how we direct that capability through efficient search, rock-solid values, and strict, undeniable verification. The most decisive question of our time isn't whether superintelligence can be built. We know it can. The question is, can it be made governable before it becomes deeply embedded in systems operating completely beyond human control? Are we actually building the stopping gates fast enough?